Hello everyone, I'm Xiangyu. Today I will present our work on switch code generation using program synthesis. This is joint work with collaborators from NYU, Rutgers, Princeton, and National University of Singapore. Programmable network device has become quite widespread and they also run at a fairly high speed. For example, Cynix LVL run at 100 gigabits per second. Mellanox Bluefield run at 100 gigabits per second, and Barefoot Tofino run at 6.5 terabits per second. It is easy to get us started with programming these devices. For example, you can read the tutorial or you can attend a workshop. But writing fast packet processing code that fit within resource constraints is really hard. There are two main approaches to writing fast programs, but none of them is easy to implement. The first one is to handcraft the fast programs, but this requires familiarity with most of the underlying hardware architecture. For example, the expert must be aware of the lookup table for FPGAs, cache and memory hierarchy for SmartNICs and CPUs, arithmetic logic unit for switches. And the second is to rely on a compiler to do code generation. I totally agree, a compiler itself will definitely elevate the difficulties of generating such code, but building the compiler itself needs significant engineering effort, which is both time-consuming and money-consuming. Because the packet processing hardware is niche, sometimes it's really hard for us to build such a team for newly evolving hardware. Therefore, our paper presents a new approach to generating code for programmable switches. To set a context for this talk, let's look at why writing and compiling fast switch program is hard. Because the programmable switch have all or nothing compilation feature, which means the compiler either fit the program into the hardware or reject it. There is no gray area inside. I'll give you an example from Domino compiler for programmable switch pipeline. For now, it is sufficient for us to regard Domino as a C* language and turn it into the machine code which will be finally run in the programmable switch. The compiler will choose the opcode and determine the input for each ALU and the value of multiplexers. What could go wrong with this setup? The Domino compiler produced different outcomes on semantically equivalent program. If you write a program in this way, Domino fails to generate code for it. However, if we rewrite in this way, then Domino can generate code for it. We call this butterfly effect, which means a small change in the way a program is written have just effect on the compilation result. And in addition, such butterfly effect also happens in some P4 compilers as well. In response to the above concerns, there are three main contributions in our project. The first one is we leverage the program synthesis tool to do code generation. And we also develop many domain-specific synthesis algorithms. The most effective one is slicing algorithm. We designed two backends. The first one is a pizza simulator and the second one is a Tofino's ASIC. We let our generated machine code to run in these two backends. At a really high level, program synthesis is to automatically generate a code that satisfies a specification. A program synthesis engine takes two as an input. The first one is the search space represented by the partial program and the second one is the specification. Then both of them will be fed into an exhaustive search algorithm to output the completed program that satisfies the specification or return infeasible if there is none. In our project, we use search space to represent the machine code skeleton, use specification to represent the high-level language program, and the program synthesis tool we use is Sketch. We believe that program synthesis can be used as an enabling technology for packet processing compiler. So let's take a look at a detailed example from Sketch. Suppose we have this example which we add the input 3 times to itself. And if we consider this partial program, then Domino can find Sketch can find the solution to it by setting the whole value to be 3. Well, the question mark here is a whole, which represents an unknown constant. If we consider this partial program, then Sketch cannot find any solution for it, which means this partial program is infeasible. Suppose we have two people. The first one is the programmer and the second one is the compiler developer. The programmer will write a program in Domino language and the compiler developer will design a partial program which represents the programmable switches capability. Then both of them will be fed into a Sketch synthesis engine to output the completed program and turn into the programmable switches machine code. Let's take a look at the chipmunk in more detail. Still, we have these two people. The programmer will write a program in Domino language because Domino preserves the transactional semantics which means as far as a packet is concerned, when it goes through this pipeline, it can assume there's no other packet inside this pipeline. He will use the state variables like count to represent the persistent switch state, and packet field like packet.sample to represent the packet header. Compiler developer will write a partial program for programmable switches. Stateless ARU will modify the packet header. Stateful ARU will modify both persistent switch state and packet header. Packet header vector will be used to store the packet header, and input marks determine which value will be parsed, feed as an input for a particular ARU, and output marks will determine which output will be parsed to the next stage. The structure is similar across stages. When we have program and a partial program in hand, we will feed them into chipbound compiler to output the machine code for programmable switches. However, synthesis will be really time consuming because the search space might be really large. This is similar to you want to pick up a needle out of a huge stick. We have to use magnifying glasses. But we develop many domain-specific speeding up algorithms to make this whole process feasible, like slicing algorithm, constant synthesis algorithm, canonicalization algorithm, and scaling up synthesis to larger input ranges algorithm. The most effective one is slicing. We can refer to more detail in our 20-minute talk or our paper. For backend for Chipmunk, we design a pizza simulator backend based on the Benzine machine code because we want to compare with Domino compiler. We also design a Tofino's ASIC because we want to generate code for real hardware. We also design a Chipmunk to be retargetable so that by designing a domain-specific language to easily specify different instruction sets capability. For evaluation part, we compare Chipmunk against Domino's existing compiler because Domino used some handcrafted rules to translate Domino's program to machine code. We also consider some other alternatives, for example, P414 or P416 compiler from chip vendors like Barefoot, but they have not supported the Domino's transactional programming model, although P416 has already supported atomicity inside the program. We also consider some open source P4C compiler, but they only support software packet processing targets with different architecture. For metrics, we really care about the compilation result, which means whether Domino or Chipmunk can successfully generate code for a given program. If both of them successfully compile them, which one use fewer resources? We pick up all benchmarks in Domino language, but we cannot directly use them because these benchmarks have successfully compiled with Domino, and Chipmunk also successfully compiled them as well. So really compare them on Domino or Chipmunk will be useless. But we really want to ask this question. If we mutate these programs, will Domino and Chipmunk still compile them? Theoretically, yes. Empirically, let's see what will happen. Actually, Domino failed to generate code for most of the mutations, but Chipmunk successfully compiled all of them. As for the resource usage, Chipmunk used fewer stages than Domino. However, for the compilation time, this is the Achilles heel of Chipmunk because Domino finished within several seconds, but Chipmunk finished sometimes several minutes, sometimes the worst case is 2 hours. But 90% of them finish within 5 minutes. We also let 10 out of 14 benchmarks run in real Tofino switch. The reason why the number here is different from previous slide is they have different arithmetic logic unit. And the remaining 4 fail to run in Tofino switch because we believe their functionality is too expressive to run in the Tofino's ASIC. We measure the speeding up effect from slicing. Actually, the slicing algorithm gives us around 51 times speeding up. To conclude, we transplant program synthesis in code generation for fast packet processing, and we also think program synthesis can enable fast packet processing like what SET and SMT software have enabled in network verification. We also develop many domain-specific algorithms to make the whole process feasible. With that, I conclude. If you have any questions or you want to reach out more details, please contact us at my email address and GitHub repository. Thank you very much.
Okay, great. Now let's move to the Q&A session. So if you have any questions, please post in the Zoom Q&A window, or you can also type your question in the dedicated Slack channel for this session. So I will start with a question from me first. So my question is that can we go beyond the all or nothing design and design a solution to measure how much chipmunk can compile a given program instead of simply output yes or no?
Hello everyone. So first of all, sorry for the low quality of this video. And yeah, so this is a good question. This totally depends on the metric we design for the compiled program versus the program given as an input. So there are several metrics, at least in my mind. First, so we know the program will get packet plus state vector as an input and output the packet plus state vector as an output. So we want to measure how many, which portion of this vector can get successfully, can get the correct value. So this is one metric to measure how much a program get compiled. And second, we can measure, so for a particular input range, the result is correct. And for another input range, the output may be wrong. So for these tons of metrics, now Chipmunk can only provide an either compiled or not compiled result. But we are in the process of designing more metrics to hopefully Chipmunk can provide more feedback if a program cannot get a successfully compiled result. We want to give more feedback for the user.
Okay, great. So the next question is from Ben. The question is, would the chipmount technique also be useful for mutating eBPF programs to pass the verifier?
So yeah, so for now we only focus for all the as I show in the slide. I only mutate all the program in Domino language, which will be their target is in the programmable switch. But for eBPF programs, we design our chipmunk be really retargetable, which means we have to write to explain the instruction set which can be supported in the eBPF part and mutate them to parse the verifier. So this part need a little bit manual work to retarget to encode the instruction sets functionality, but I think this can be done in our current setting.
So okay, so we will do one more question. So the last question is, can chipmunk support multiple chains in ASIC? And does chipmunk support complex benchmarks such as switch.p4?
Right. So currently, chipmunk can only support one ASIC chain. It cannot support multiple ASIC chains. And for now, all the benchmarks in our experiment are simply written in Domino language, which only capture one action portion inside a P416 or P414 program. But for more complex benchmarks like switch.p4, they support a lot of match action part, and a lot of actions inside that benchmark. Currently, we cannot support it.
All right, thank you again. So I've got a few questions here. So just a reminder, the Q&A button at the bottom is how kind of we're preferring to take questions right now. We've got one here that says, they're curious about why Chipmunk is using more time than Domino. Can you expand on that?
Right, so this is a really good question. Actually, the content is put in my 20-minute talk or like the backup slide. So if we take a close look at what Domino does, is Domino will use some rewrite rules to rewrite a given program into the intermediate representation, which is shown in the DAG file. And we can see each rectangle represents a computation for either persistent switch state or the packet header. And to preserve the atomicity, each rectangle will be mapped to one arithmetic logic unit in Tofino switch. So actually, this is what is done by Domino. Basically, Domino only need to do code generation for each pieces, but Chipmunk takes the whole problem as an input and do the code generation for it, which means Chipmunk have to take care of the whole program, but don't only need to take care of all pieces of the program and group them together. That's why the search space of Chipmunk is much larger than DOM. So which caused the Chipmunk to use more time than DOM.
Great.
Yeah.
Thanks for that. I had a question I was curious about, actually. So, you made a nice case for why you want to do this for switches in P4. I'm curious whether you think we should be doing a similar approach to replace, for instance, GCC, like a C++ compiler.
Right. I think compared with some we call rule-based compilers, Chipmunk will have more completeness. But if we want to try to replace something like GCC, it totally depends on the synthesis time, because nobody wants to spend around several hours to waiting for their compilation result. But if in some domain-specific case, well, they only need to compile not that frequently, or we can design a lot of domain-specific speeding up algorithm to make all these things feasible. For example, finish within 1 or 2 minutes. I think at least they can help a lot in GCC's part.
I see. So yeah, my follow-up was going to be whether there was some fundamental difference about the domain, but I think you touched on that a little bit. Thanks.
Yes.
So there's another question here. So also dealing with the compilation time. So what were the main factors that were causing that increase? So for instance, in the stateful firewall, and what do you envisage as P4 programs evolve? Are there any issues with future P4 programs?
Right. So this is a good question. My interpretation for this question is basically which feature or which factor of the given input will cause the increase of the compilation time. Because also in my, I guess in my slide, they have different compilation time even for different benchmarks. So basically, it totally depends on what computation is inside a given program and the structure of the given program. For example, if they have a lot of if-else statement or their computation is very complex, or generally speaking, if the line of code is very long, then we can say this program is complex. That's why we have to give more computation resource. For example, more computation stages and more arithmetic logic unit per stage. Then the search space may increase and the synthesis time might be longer. So that's basically, I think the main factors causing the difference between compilation time across all these benchmarks.
Got it. Great. And then I think we have time for one last question. So in addition to the Tofino switch, does Chipmunk support code generation for other switch hardware architectures?
Right. So this is also a really good question, because in this slide, we design our Chipmunk to be retargetable. So of course, this can support code generation for other hardware architecture. If you are very familiar with the instruction set in that hardware architecture, and basically you have to familiar with the computation supported by a particular instruction set and the communication across stages in the new hardware architecture, then we can design it, and our domain-specific language can help you generate the sketch file and do code generation for that structure.